So before we begin, right, I should show you this one. These are the questions that are collated from the Google Sheets, and we have a total of, I did not count. I just don't bother to count. Let's go by how many questions we have. Right, so if you're wondering which question you need to look at is question 1, right? We have 6 questions there. Right, so you may want to take out your question paper, the TYS, and look at where the questions are planted. Right, so 1C, 1E, and 1F.
Yeah. Oh, I found it. Amazing.
Chemistry. J2, yes, yeah. All right, okay, so question 1, we have 6 questions. Question 2 is the big one. And I was counting, I counted 14, especially 2F part 3 or 2E actually. Okay, the big weird question that we have there, right? Then we have 3 questions on question 3, 3C and 3D, right? Question 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 questions. Okay, and finally we'll end off with question 5, 3 questions. Right, so this is the layout for today, right? I already planted the questions to the respective parts. So let's begin according to sequence, right? So let's start from question 1. Okay, everybody can go to question 1C. Or take a look at question 1 first. Okay, by the way, before I begin, can I have a show of hands? Okay, everybody, just want to gather some impromptu feedback. How is this paper to you? This good? This is and this is meh. Which one? Okay. Doable? Doable, right? This paper is okay, right? Except for one, a few certain parts that is a little bit trickier, like this one already. Okay, the one on the screen, 1E. Okay, some people already struggle here already, right? Okay, so to be honest, this paper is not the toughest one yet. Not yet. Okay, you will see a very tough one soon already. Okay, so yes, you're here. All right, everybody, let's look at question 1C, part 1. Okay, draw a fully labeled diagram, okay, to measure the standard electric potential of the cobalt 2 plus cobalt half cell. And part 2, we are going to do a solution containing Fe2 plus and Fe3 plus added, right? Okay, so I planted the question to the part already. So let me find the part out. And okay, this is the time where I want you all to try and answer on my behalf. Try out and see whether you can answer your friend's question. 1C part 2. Okay, look at 1C part 2. May I know why do we choose these 2 equations? And which 2 equations is these 2 equations? Okay, anybody struggling with the equation to choose? Okay, now if you're struggling, right, the hint from the question is where? Right, now if you look closely at the question, right, the question says, draw a fully labeled blah, 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 of a cobalt 2 plus cobalt half cell. So your job now, right, is to think, how do you draw this half cell? Do you know how to draw this half cell? A cobalt 2 plus with cobalt metal half cell. Okay, I can finish this half cell drawing in 10 seconds. Ready? Want to try? How to draw this in 10 seconds? Let's try. Ready? 1, 2, 3. 1, 2, 3. One more palladium cube. Oh shit. Cobalt 2 plus equals 25 degrees Celsius. Cobalt metal done. Okay, there's no H plus because if you know the half equation, right, there's no H plus here, right? Okay, so with this idea, you roughly know what's on one side of the galvanic cell. This is the one that's helping you. They say now you have a mixture of Fe2 plus and Fe3 plus, right? Do you know how to draw this half cell? I can finish this in 10 seconds also. Ready? How to finish in 10 seconds? I'm going to play cheat. I'm going to play here. 1, 2, platinum, 3, or carbon. Or this is one more palladium cube, 5, Fe3 plus, and one more palladium cube, Fe2 plus, and then 25 degrees Celsius. Done. Okay, so you need to have an idea on how it forms in your head already. Okay? Right, so if you're like struggling with this, it means that you are not reading your galvanic cell lecture notes, the starting part properly. Not yet. You better reread that. Okay, right. Now, here's my answer to this. The question actually tells you it's Fe2 plus and Fe3 plus. So would you choose this half equation? Answer is no. Then your question next is, how do I know this equation is chosen or supposed to be chosen by me next time? There's a simple rule in the question that I'll give you. Okay, when do you choose this one? When would you choose this one? When they tell you you have to use an iron electrode. Okay, that's it. That's the answer. When you need to use an iron electrode, the metal itself, then this is the one to go for. But this question did not say that. Okay, just two ions, okay, all placed in the same solution. Okay, so that's my answer to this part. All right, okay, so that's it for 1C part 2. Okay, I hope this one is useful, right? And if you need more help on why certain equations cannot be chosen and so on, right? Okay, you can let your tutors know. Okay, otherwise I will move on from here. Okay, right. Next one is one, not this one. This one actually quite, this one has no questions. So I was expecting questions for the energy cycle, but seems like it's fine. By the way, right, do you know what's the official name of this diagram? There's a name to this diagram. It's a cycle. Born-Haber cycle, thank you, right? It's a Born-Haber cycle. Do you know that Born-Haber cycle is meant for a classification of compounds? If you read your notes carefully, it's only for ionic compounds. If you have covalent compounds, this is never used. Just think about it, right? Okay, look up for those details. Okay, let's go on to this one. This is an interesting question, right? So 1E is about the empirical formula thinking, right? Yeah. So I have my response to you. So I will spend a little bit more time here, so get ready for it. Okay, so the formula is cobalt H9N6O6, right? Okay, and we have a lot of questions about how do we come up with the formula for A and B. Right, now there are people who actually post that they have struggles with this, but those of you who did not post anything, you are the silent so-called majority. Are you also struggling with this? If yes, let me teach you how to see it, okay? Right, and there's one of you who said, I do not know empirical formula. No. But by the way, empirical formula is the lowest formula already, the lowest common multiple thingy, right? So that means, right, if you want to know why empirical formula can be ×2, it's because that's the molecular formula. Okay, secondary school stuff, molecular formula and empirical formula. And empirical formula is a ×1, and molecular formula can ×2 all the way up to infinity. Okay, right. Now let me show you how it works here. Okay, you can see I have a lot of scribblings already. All right, okay, there are two ligands only. Can you highlight for yourself? The two ligands is ammonia. Okay, ammonia and nitrite. So if you were to look at your formula for compound A and B, right? A is this one, right? So how many ammonia can you see already? If you look closely, there's only 9 H's. 9 H's definitely go for 3 ammonia, right? Because all your H's go or comes from ammonia. All your oxygen comes from nitrite. So those numbers will help you to see that in this formula, right, you have exactly 3 ammonia and 3 nitrite. I hope this makes sense to you. You look at the hydrogen and oxygen to help you to see how the nitrogen is split up. So the 6 nitrogen are split up into 3 and 3. After this, you just form the formula. That's it. That's the answer for this really. Because how do you know? Because if you were to do a MR calculation, right, this is exactly 247.9. Okay, so which means compound A, you just need to merge all these together. So when you merge all these together, do take note, okay, that this part here, let me highlight. This one and this one, right, they will negate their charge. Do take note, 3 times -1 and 3 plus, right? Sorry, it's 1 minus. 3 times 1 minus plus 3 plus. So they will negate and turn into a neutral compound. Okay, so do be careful about this part. All right, so that's why if I were to go to the answer that you see, they just merge everything together as a formula. Everyone okay? Yeah, all right. Now the problematic one is compound B. So A, okay, right? If you understood how A works, B actually is easier because B is ×2 of the formula. That's it. There is twice, right? So actually quite easy. I want to show you it's very easy. Okay. Have more faith in yourself. You just times 2 everything. When you times 2 everything, and you learn that cobalt technically can form what's that? 6 coordinated complex ion. That means you can take these 6 and form a complex with 1 cobalt 3 plus, and then take another 6 and form the next 6 coordinated transition ion, right? Complex ion, right? Then you roughly know how to form the next formula already. Right? You take 1 cobalt with 6 ammonia and try to turn it into a complex ion, right? And then take another cobalt with the other 6 nitride and form the other one. Just be careful about this one, the net charge, huh? Right? This one is 3 minus overall, and this one is 3 plus. And it fits the question, because these two together, technically this is one huge big cation and one big anion. Just turn it into ionic compound. That's it. Okay, that's it. That's all the question is asking you to do. Okay, but if you are not taking it literally, right, you will be shortchanging yourself. You just cut yourself short in your thought process. So you need to just follow the question and have faith in it. It's trying to tell you literally. Okay, cannot. I take it as it is, and you should get. Okay, let me go back to the answer. That's my answer. Yeah, you should get this. So I hope this one starts to make sense why it is like that now. Okay. All right. Actually, I've run out of my explanation space. I do not know how to explain further. All right. So that's about it. Okay. Your job next is actually, if I want to expand this question, right? Do you know how to draw the ions out? You have just finished your TE tutorial. You should know how to draw this ion and know how to draw this ion. You should. It's all octahedral. Do you know how to draw octahedral shapes out with the dash and wedge? Yes, right. Some of you have the image in your head. That's the exact same picture you should go for. Okay. The only thing I have concern is this is the homework I have for you. Everybody, I'm not going to tell you the answer. How do you bond the NO2 to the diagram? Is it the N that bonds to cobalt, or is it the O that bonds to cobalt? I want you to think about it. Okay, this is nitride, by the way. So is it the nitrogen that bonds to cobalt? And that's the one that forms a daily bond, or is it the oxygen? Please think about it. Okay, any query, just ask your teachers. You need to know this. Okay, ammonia you all know already lah. So it's a bit too easy. I want you all to think about this, the nitrite. Okay, can. All right, I'm gonna move on. Okay. 1F part 2. Okay, this is the titration area, right? With iodine thiosulfate, and there's a reaction with manganate. How do I know how to connect the manganate equation to the iodine equation? Ooh, okay, good question. Right, you have to treat it like a standard titration, like practical. Right, so if you all look at the question for 1F, okay, is that you have a sample of preserved meat. Okay, the meat has sodium nitrite inside, so you use distilled water to dissolve the sodium nitrite. Then you take manganate, now colored in purple. It says that this manganate you add in excess. Why do you add this in excess? So what procedure are you doing here? There's a name to this process. This is called back titration. I hope you all saw it's back titration. You purposely add the first reagent in excess so that you can test out the remainder later on. Okay, yeah, the logic is there, right? Then your iodine is the titration for the remainder. This is the crux of this question. Okay, it's not coming. But the one in yellow, by the way. Okay, so you're using iodine as the product here. Okay, so iodide reacting with manganate, right? So iodide, right, is also in excess. Oh yeah, came out. Okay, do you realize this is a very interesting back titration? There's an official name to this. It's called double back titration. Okay, call it back titration. Okay, you're using a back titration to solve the previous back titration. Okay, so if you're wondering how do I link up my iodine, right? It's because my iodine that was in this step, this is the second titration. So it is the first titration. Hey, my stylus is, sorry, my stylus is not working. This is second titration. So the first titration is trying to react iodide with manganate and turn into iodine. This iodine appears here. And then you use thiosulfate to react with iodine. So how do you see the link from iodine to manganate? Is because iodine is the product from the iodide and manganate. So you work backwards, okay, and find the mole ratio, and then that's how you link up iodine with manganate. So if you're asking this question, right, is that you are stuck between the first and the second titration that link. Okay, the iodine from the first titration, okay, is going to help you to predict how much manganate was left behind from the very first reaction. So how many reactions are there in total in this question? How many reactions in total? There's technically 3. What are the 3 reactions? Maybe let's have a clear idea. The 3 reactions are, okay. Maybe I've drawn too much already. Okay, let me help you out again one more time. The first reaction is where? Sodium nitrite and manganate, which is this one. This is the very first one. The second reaction is, I'm going to use red color. The second reaction is this one got leftover. So the leftover and iodide reacts. Okay, yeah, make a mess already. Okay, the leftover manganate and iodide will react. Then they will form iodine. That's the second one. Then what's the third one? Let's change color, orange. Okay, the third one is the iodine from here. Okay, yeah, it will appear here, and then you use thiosulfate to help you see. Right, so there are 3 things or 3 that reactions that is linked up to each other in this manner. So you just work backwards. Okay, right. Okay, so far there's only one question for this. So it seems like majority of you can handle this quite okay. Can I? Right. You all manage to get the answers? Can I? Right. Okay, I'm going to close question 1 in this manner now because question 2 is the main problem, the biggest problem of the paper. Right. So let's go for question 2. Okay, and then let's solve for the first part already, part A, which is about basicity comparison. Right. So we have a pretty interesting question asked, and I think all of us should know the answer to this. Okay, let's look at the first one, 2A. Okay, so this question is trying to compare 3 compounds, but one of them is eternamide, which is an amide. Then you all learn amide are neutral. The problem is, how do I know, should I see this as a neutral, i.e. does not act as a base, or should I see this as a weak base? Okay, so here's our official stand, is this is how you should answer it. If you are looking at this question is number 2, it's being forced to be compared as a base with other amines. In this case, you treat it as the least basic amine, so or compound, not amine, least basic compound, even though you know it's neutral. Then there is another type of question that can come out as a solo question. Solo means what? What is eternamide all about? Yeah, if you are just talking about the amide by itself, then it has to be seen as a neutral compound. Oh, is that clear enough? Yeah. So if you are being forced to compare it with other things like this question, then you will have to follow the question direction. Yeah. So it depends. That's the answer. Okay, can I? It depends. Really depends. I hope this year's A-level is nicer to you. Nicer in terms of giving you the question that like, oh, I understand what you're trying to ask. Okay, you know that this 2020 is A-level, the question they ask is like, oh, what's going on? I don't even know what's going on sometimes. Okay, right. What's the other one? May I know why the extent of delocalization of the lone pair of electrons into the CO double bond is greater than the delocalization of the benzene? Okay, valid question. Are you ready for something hardcore now? It's theoretical stuff now. How come the delocalization into the C double bond O is better than the delocalization into the benzene ring? Now, class, if you are following that, oh, delocalized into C double bond O is 2 atoms versus delocalized into benzene ring is 6 atoms, shouldn't the 6 atoms be better at delocalization? Right, more atoms, right? You can like suck it in the black hole, right? Right? No, no, that's not how it works. That's not how it works. Okay, let me show you how it works now. Okay, are you ready for some hardcore stuff? Hardcore meaning this. Okay, if you really want to know how delocalization works, technically there's actually a computer program that shows the electron distribution. This is called the electrostatic potential map. Okay, the more red it is, the more electrons it has. The more blue it becomes, the more electrophilic it becomes. That means electron deficiency. Okay, so if you all look closely, right? Okay, the way your nitrogen's lone pair, which is here, get delocalized here, is not even. It's super red on the oxygen side. Why? A-level concept. Why is it so red, i.e. electron rich on the oxygen? Oxygen is the most electronegative element right now in the compound. So your lone pair technically, right, reside more towards the oxygen side. So it's delocalized, correct, but it's more on the oxygen area. So our answer to you is, it is not available for photonation. Yeah, it's that bad. Yeah, it got delocalized to the point that it just cannot be a base anymore. Okay, so I'm trying to link up what real world data is towards what we have in our node. So this is how we conclude it as it is not that available at all. But if you are looking at phenylamine, the delocalization does happen, but it is not as effective as this, right? So if you want to go and Google search an electrostatic potential map for phenylamine, it will look like this. So that's why I'm trying to see whether I can put these two side by side to let you see how reddish this part is. Okay, you need to see the nitrogen a bit reddish. Reddish means what? In our A-level concept is more available or less available. The more red it is, the more available. The less red, the less. Then it is not red, it is not available. Okay, that's how we actually come up with all these phrases. I hope it starts to make sense now to you, right? It's based on this. And then you realize 6 carbons is worse off than 1 oxygen. Okay, 6 carbon technically is not as good as 1 oxygen being there in terms of the localization of the charge or the lone pairs. Okay, so that's roughly how it works. So if you're like, I still don't get all this, then maybe perhaps you can just take it as at face value, the explanation given in the notes. Is that okay? Yeah, the electronegativity of the oxygen actually is the main factor here. So yeah, that's one of the key reasons. Everyone okay? Right, next up. Okay, this one is 2B. May I know how we derive and structure? Oh, this one. Do you know what is that additive bond? Okay, I think we need to be a bit more sensitive already. Okay, class, if you see nitrogen, you need to know that there's a something there. Lone pair. Yes, you cannot, huh? What's that? You see nitrogen is like ding, lone pair. Then lone pair can do what? A lot of amazing stuff, nucleophilic stuff Lewis base can attack something, right? Ligand, right? All this, right? Then you see aluminium. What's your first word you think about for aluminium or first term? Electron deficient. You should have that word. When these two things go together, ding, dative bond will have to come out in your head already. Because to form a dative bond is those two ideas, a lone pair and empty orbital, which is electron deficient. Yeah, this is the condition to make it work. So if you're asking this question means you haven't gotten the awareness yet. You need to get that awareness. Be sensitive to it already. Everyone okay? Actually, there's another question about dative bond later on. I think it's in question 5. There's another one. Okay, but I'm done with this. Okay, and by the way, the next question, the thing about, okay, if you really want me to deep dive this question, I can go a little bit further, is that the amine, right, tells you it forms a neutral compound. Dun -dun, neutral. So you cannot make it an ion anymore. You cannot let any electrons move in and out. So the only way to form a collective compound is to merge it with dative bond. Okay, that's a key word. Okay, next. Okay, okay, we have a lot of organic questions. Okay, 2F ready? Is it 2? Yeah, 2 is coming up soon. That's the big one. Okay, this is the one I need to talk about in a bit more detail. Okay, so 2C for step 3, which is this reagent condition, it throws a lot of people off. How come the answer is like that, right? Limited ethanolic CH3CH2Cl, comma heat. Why must I put limited? Which I say yes, you need to put limited. And how do you get the limited? Okay, and let me show you how it is done. Right. So if you look at the transformation, which I just do this, right, is that this is the part that turns into this, right? Okay. Then you're wondering under nitrogen compound, have I ever learned NH2 turning into this weird thing? Answer is yes and no. No, because you never see this in the nitrogen nodes. Yes, it's because you see in the RX nodes. Do you know that in your RX nodes, page 14, amines is there. This is actually the collaboration between RX and amines. We can put this one in amines, by the way. Okay, yeah, it's actually just a reverse. It's the same thing, but just change the subject only, right? So in your RX notes, when you are reading this as a RX, right, you are so focused at RX being the main subject that you forgot that amine can also be the main subject, depending on your choice. Okay, so here, let's look at this diagram, this one. Yeah, I want to use this as an example. So in our notes, right, we say this is our main subject because we happen to learn RX. So what is our choice is we use ethanolic amine, right? We say ethanolic amine, right? What happens if I just switch these two around? Then you become ethanolic RX. The medium stay put, but the choice of the subject change. That's it. Right? Everyone can get the reason why is it ethanolic RX already? Can I? All right. Now I'm going to go into this. This is actually the more difficult thing to explain. Limited. Why is it limited? Okay. Now somewhere before your page 14, right, is page 13. Page 13 for say this. Oh, sorry. This whole part. Yeah. This is the last line on page 13. So I try to show you that. Right. Actually, there is it's something like your FRS. If you do limited CL2, you get one type of outcome. You get excess CL2, you get another outcome, right? This is the same idea. So now you have a choice whether you want to limit the amine or limit the RX. So if you limit the RX, you get more primary amine. Primary amine means in this case it's monosub. That means you sub in once, you don't let it continue the nucleophilic substitution, and then that is your majority of the product. Okay, so if you look at my question, okay, ready? I'm trying to do the link now to the question. If you look at the question, it's monosub. You only monosub it. Your monosub means this situation. You want to have excess amine. Okay, this one can be switched to amine. Excess amine, or see this as limited RX. This is not an easy concept to grasp. So you need some time to really sit down and figure this one out on your own. When this is limited, what happens next? When that is limited, what happens next? All right, you need to really sit down and think about this. Okay, this is on page 13. So I would strongly encourage you all to read page 13 and 14 of the RX notes. Okay, when monosub happens and when polysub or multisub happens. Okay, I hope it helps. Then move on. Okay. May I know if I have to consider the bond angle for 2D? Do I need the bond angle? Do I need the bond angle for this? Yes. Yes. A level. Yeah. There's a lone pair here, by the way. You know that you can do C-trans here. But in a certain sense, but no, this one cannot be C-trans. This one cannot be C-trans. You don't know how a double bond works, right? You make things particular. Okay, anyway, I'm not going to go through that one. Okay. Anyway, okay, so you're supposed to do a bond angle. Okay, this is the interesting one. 2E part 1. May I know the brain way to come up with the structure of G and H? Okay, which is this part. How do I get the structure of G and H? Okay, so I actually say I don't know, because what is brain way? So I Google search What is brainwave? Apparently it's an app. Okay? To analyze your habits and routine. I don't believe the app can do this. So I'm going to presume that you're talking about how do I get to the structure. Okay? Okay? I don't have the app. I refuse to download the app just because of this question. Okay, anyway. Okay. Those of you who are observant, do you know why I color code in this manner? Can you see or not? Okay, let's give ourselves about 30 seconds. Look at the question again, because I will be very technical in my response here. So I would like you all to look at how my color coding work. So the red, no, red, what red? The yellow part is the alkene. The blue part is the diazo compound, right? I think it's called diazo compound. Yeah, the diazo compound thing, right? So the blue part is the leftover from the diazo. So the nitrogen molecule leaves, and then the blue color part forms the triangular shape, right? Okay, so here's the thing. So in order for you to see where's the alkene and where's the diazo molecule, right? The logic is you see a triangle, and you got to choose which side belongs to the alkene and which side belongs to the diazo. There are three ways to see it. Like this, or like this. Right? There are three ways, right? Mathematically. Okay, I hope you all now understand why my answer structure. I'm the one who came out with this answer. Yes, this one. Because I have to color code it. Okay, right. So these are the three ways to see. So the red color is meant to see the alkene. That means if you were to take away the black bonds, because in order to form the triangle, you have to form the bonds to form the triangle, right? So if you take away the black color part, the bonds, you get back the alkene here in red and the a diazo one here. Okay, I'm going to erase this so that it doesn't complicate. Right, but you have an issue is that you do not know which one is which. So here comes the biggest clue in the question. The clue says G must be a hydrocarbon. G must be a hydrocarbon. If you all did not see it, is here. There's a statement here. G is a hydrocarbon. So you got to choose the side that does not have the ester. Okay, let me go back. You have to choose the side that doesn't give you the ester. So if you were to take the upper two and see how the red color was trying to form back the alkene, right? You will have accidentally added in the ester. Likewise for the other diagram. So hence, in order to form back your alkene properly, you have to go for the bottom root. Okay, and then the top part here, this is the one that was supposed to be in blue, will turn back into the diazo compound. Right? So what you do now is you just split this one out. Why is it all highlighted? Okay, you split it all out and put a double bond here. This is your compound driller. Yeah, that's it. It's actually quite simple. Cut the correct places and get your alkene by putting one more bond there. How do you solve this blue color part? You just add back your N2, right? Yeah, that's it. You just add back your N2 to this part, you get the answer. So that's why the answer is this. Okay, add back the N2. All right, so if you have seen the soft copy, right, with the color coding, right, it's supposed to be helping you. Okay, so I'm just trying to address how to understand or interpret this part. Okay, and I believe this is the first really tough question for this paper. This is the very first one, actually. But I think it's an interesting question. It really forces you to think properly how should view the compound in different ways. So yeah, this is something about how you understand triangles, in short. Okay, right. I'm done with this already. So anyone has any question here? Okay, you can, feel free to ask Mrs. Hua. She's quite busy now, so wait for your turn. Okay, any more? No, right? Yeah. Okay, let's move on. Okay, I hope you all also can do the chiral carbon on the ring. It's been a while since we have done a question about finding chiral carbons on a cyclic ring. This one is a triangle, so it's quite okay. But we have like many rings fused together. Do you know how to see the chiral carbons for that kind of examples? Okay, you may have to go and reread that part also. Okay, now I want to go into 2F now. Okay, this is a interesting one. I Google search what is angle strain. Actually, do you know what's angle strain? What is angle strain? I see. Okay, here's the thing. Okay, I see a lot. You can hear me? I see a lot of you say, like you just use your hands, right? Angle strain, right, operates both ways. If it's too narrow, it's an angle strain. If it's too wide, it's also an angle strain. Angle strain basically means deviation from the ideal bond angle. That's it. It can be more acute or more obtuse. Both are equally bad. Okay, so your understanding from VSEPR says that it tries to go for its ideal bond angle. So which is what? Tetrahedral is what's the bond angle? 109.5, right? Trigonal planar? 120, right? I mean, that's the whole idea. But the values, right? If it drop, if the angle is too small or too wide, it's also not good. No good, right? Okay. So here's the thing. What does angle strain create? It creates weaker and more reactive bonds. Okay, I think you all should at least get this idea. It will cause the bonds to become weaker and actually more reactive because they are weakened, so they want to form stronger, more stable bonds next time. So they'll find an opportunity to break and form better bonds. Okay, by the way, this is from Google. I trust Google. Okay, so how does angle strain affect bond energy? Right, this one, I don't think Google helps a bit. I'll give you an idea how it works. So sigma bonds. What's the definition of a sigma bond? What's a sigma bond? I think you all can head-on overlap, right? Blah, 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 all this, right? So the best head-on overlap with a hybrid orbital is like that, right? Right? Direct head-on overlap, best, good. But in a triangle compound like cyclopropane, right? You cannot do this, and it doesn't work like that. It's like you know what I'm trying to do? It doesn't work like that. You cannot do head-on like that one. The bond angle is 60. Cannot. The repulsion from the orbitals will affect it. So cyclopropane has a very interesting thing. We call them the banana bonds. The bonds actually bonds like that one. Sorry. Okay, whatever lah. It will look like this. They will bond at a diagonal instead. They will repel, but they will still want to stay intact. So it actually overlaps sideways, diagonally. Very weird one. But diagonal is not effective. It's not as best as a head-on. Okay? So the whole idea here is I want to showcase that angle strains can affect the way the orbital overlap is. Yeah, and makes it less optimal, and then hence it weakens the bond energy in that sense. So for the one who is asking how it affects bond energy, it's about the ineffectiveness of the overlapping. Okay, that's how it was linked up in this sense. I just want to showcase that one today. Okay, now then all your theory, right? Everything is about bond energy, right? The one you learn your notes on, it's because we assume everything perfect. Just nice. Okay, so we do have this gray area here. Okay, this one, just have a awareness about it. Okay, right, this one, all right, okay, part 3. Wow, this is the question. Okay, should I write all these words? Should I draw diagrams? Okay, I want to let you know, may I know if I can draw the graph and state the draw? Actually, yes, you can, but if you know how to label everything, that's best. But the problem is, if you miss out one, then your answer is not adequate, right? This is another one. Can I use half-life to justify the first order? Can I use T-half to justify the first order? Okay, for this part. Because there was a question about plotting initial rate, right? To get a straight line passing through origin, right? So can I use the T-half? That means the T-half is constant, but they are being halved. Okay. The answer is you cannot. Why? Not because you are wrong, but the question asks you to use initial rate data. The question forces you to do initial rate method. You do the other method. Then you're just shortchanging yourself. Okay, Dana, that's the answer. You cannot, just cannot. The question forces it. So class, do you have to know initial rate methods also? Yep, you get it. They are forcing it in one direction in this sense. Okay, all right, next. Then a very small question here. I think it's just a quick one. Okay, I'm sorry, it's a bit above. All right. So if you want to edit the answer here, the question is, can I have a positive sign here? Actually, my recommendation is please put in the positive sign. I agree, it should be a positive sign there. Because if you want to be consistent with endo and exo, just make it negative and positive sign off. Just show out. Okay, it will help out. Okay, so can you just add this positive sign into your soft copy, at least to help yourself to see why it can be, it should be done. Okay, right, I'm going to move on to question 3. There's only 3 questions in question 3, so I think I can finish it quite fast for question 3. Oops. Oh no, what's this? I shifted the, okay, no. All right. Okay, let's go on to 3. Oh, you came down again. Okay, 3C. Everybody, can you look at 3C? Why? I hate OneNote. Okay, how to go about step 3? How to go about step 3? How to go about step 3? You're asking about this one. How do you go about it? First of all, do you know that Q is an alkene here? Yeah, Q, you will form an alkene because you eliminate water, right? OH and a H here. You eliminate this, then you turn into this. Then you want to add a Br, right? And a H here. This is a CH3, by the way. This is a CH2, by the way. So yeah, you need to add a HBr. So it's electrophilic addition. And the answer is a Markovnikov major product. I hope you all still remember what's Markovnikov rule. What's Markovnikov rule? Oh, long time never hear already. Okay. Right? Okay, so yeah. How do you do it? Yeah, electrophilic addition. The problem is, if you're asking this question, is do you even get compound Q correct first? Because if you don't get it, then you cannot see it. Pretty sure. Okay. Right. Next. What's this? May I know why can't initial concentration of HA 3D be used to find molecular mass of HA? Oh, another brainwave question. May I know the structure? Okay, I don't have that. Okay. Wait, hold on. What's this question? May I know why the initial concentration of HA why can't it be used to find molecular mass? I have no idea what you're talking, but let me try and see whether I can solve it. Is that this question, right? All right, okay, let's try. Okay, you have a sample, right? Let me know again if I answer your question correctly. 1.76, right? Not all dissolved. Not all dissociated. It's a weak acid, by the way. And the 3.28 definitely is due to the partial dissociation, right? So your acid cannot take 1.76 as the original amount for the H+. Cannot. It's not. This is the biggest misconception that you can have for a weak acid. You dump a weak acid in water, only a small fraction dissociate. The vast majority stay put as the molecule. So you need to know this. Okay, you cannot assume that 1.76 is that 3.28. No. Okay, to be honest, 3.28, which is the H+ concentration, right, is way lesser technically than the HA that is left. That means the majority of the molecule that's not dissociated. Okay, so it's only a small fraction. Everyone okay about this? Okay, do be careful about this. Right, and may I know the brainwave to HA? I can show you the brainwave. The brainwave is, my brain tells me this is 88.2. My brain also tells me you need an acid, which is 45. Then my brain tells me I have to solve it here, right? So left with 43.2. As a chemist, 43.2 is 3 carbons. How do you know that? 12 times 3. No, not there yet. I see this as 15 times 3. How come 15? Actually, it's CH3. CH3 is 15. CH2 is 14, right? So it's just agar. It's about 3 carbons, right? Right? 15 plus 14 plus 14. That's it. Nice about there. Right? Okay, then your next clue is, why must it be branch? I think you all know already. Some of you already saw the answer. Yeah. Keyword. 3 carbons, how to branch? One way only. I read 3 carbons to play with. To branch it out, there's only one way. Okay, that's all it does. Nothing much. If you have 4 carbons, then you have multiple ways really. Yeah. So there's only one answer here. Okay, I'm done with question 3. So it looks like question 3 is the question to go for 50 marks. Okay, next one. What's this? Oh, okay. Okay, everybody, this is a good question. I remember already. This is a pretty important question. All of you should know. How come I keep shifting on? May I know if I can use the concept of steric hindrance to talk about tertiary alcohol halide, which means cannot go through SN2, hence I need to go for SN1. My answer to you is the examiner's report say your answer is not good at all or not enough. Okay, now if you look at the examiner's report, right, it says that most candidate, middle part here, most candidate actually links out steric hindrance, links out steric hindrance to the mechanism, but the fewer candidates, right, actually can provide explanation due to stability of the carbon. This is actually the more important factor for SM1. So if you want to explain why one compound go for SM1, stability of carbon is the main answer to go for first. Okay, so which means what? More R groups, more electron donating effect, then disperse the positive charge. They want the answer first. Okay, I hope it helps. Okay, before you say the steric hindrance doesn't allow you to go for SN2. Yeah, right. So that's my take on this. Okay, right. I don't think I have any more for 4A. Okay, let's go on. My stylus running out of juice already. Okay. May I know 4B, why do we need to divide entropy change by 1000? I also don't know. Don't laugh. A lot of you forgot about this. Why? Hint. What's the units usually for entropy change? Joules per Kelvin per mole. You all do not know the units, right? Joules per Kelvin per mole. It's always in joules somehow because it's a nicer number. It's in hundreds. So if you see your delta S in the hundreds, it's joules per mole. But your delta H, delta G, all kilojoules per mole. You have to divide by 1000. That's it. No choice to make things standardized. Otherwise, everything times 1000 also can. Right? You can change everything to joules per mole. Also can. But make sure your consistency is there. So yes, you need to change it to kilojoules per mole. 4C part 3 and 4C. Well, I have a lot of question mark here already. It's like I'm just wondering whether you have read your notes. I got a slight suspicion. Okay, 4C part 3 and 4C part 3 is about buffer. Is it buffer? I think it's this one. Yeah, part 3 has no equation. So I think it's this one. Then tell me why must you use full arrows here? Answer, because this is how a buffer works to remove the additions. Which page of your buffer notes says this? Not buffer notes. It's not buffer notes. Wrong. It's ABE notes. Page 23. Do you know that in order for the addition to be taken away by the buffer, you have to use full arrows? Okay. All right. If you're asking this question about full arrows at this stage, means this is your weakest chapter already. Please repeat this revision. Yeah, this is not helping you. You better do this properly and understand when a full arrow is used and when it's not. You really need to know already. Okay, it's when the buffer is acting on it. Yeah. Yeah. All right. Okay. I have about 3 minutes left. Okay. 4C part 3, revise. 4C part 4. Oh, this is the one. Okay. I think a lot of you, I actually don't know what you mean also, but anyway, I think a lot of you don't really know how to form HSO3 minus the formula, the Lewis diagram, right? Okay. I think you're asking how come it is like that. Okay, so class, you better buck up now. Please Google search Lewis diagram and find how the H's are bonded. These are all Google images, by the way. Do you notice that the H's are bonded to the O? Let me use a laser pointer. Okay, here. The H's are bonded to O. So when you use it as an acid, the OH bond is broken. Same thing, this is for H2SO4. The OH bond is broken up. Right? So therefore, how do you draw a sulfate ion? Let me try this. How do you draw a sulfate ion? You will see the middle part here, right? So a lot of you say sulfate got 2 triangles to draw, right? Do you know where the 2 triangles should appear now? The triangles is your hydrogen's electron. So supposedly there's one triangle here and there's one triangle here. That's why we keep marking you down if you put your 2 triangles elsewhere. Yeah, you get my point? If you anyhow put them anywhere else, it's wrong. It's because of this logic. Okay, so please see the acid and learn and memorize that, and then see how the triangles so-called appear. Yeah? Yeah, okay. I will have to move on. Sorry. I have about 1 to 2 minutes more. Okay, this one 4D, I think I better answer you through the Google Sheet. This one is a little bit of a fundamental problem. Is that you don't times 2 here. IC table, never times 2 here. Number 2 here means the ratio of this acid converting, sorry, not reaction, but it's a reacting ratio. More ratio is reacting ratios actually. The proportion of what turns reacting to what to turn to what, how much of what. Is a ratio thing. It doesn't represent this one. It doesn't represent the original concentration amount. So I think this one I will address that through the Google Sheet. Let me answer that there. Okay, and let me see. I have 4D part 4. Okay, most likely this will be my last question. Let me see. Do I have any more after this? Dainty bonds. Yeah, there's another one. Yeah, it's in. Okay. This one is the somebody else actually don't know. Somebody here don't know how to draw this. Okay, so that's why I want to say. Yeah, okay, let me see. All right, okay. I think I will have to stop at this last question. Give me 1 more minute, then let's settle this. Okay, now I want to showcase that the hydrogen bond between water and the acid for 4D part 4 and the acid itself, right, is actually the same type of hydrogen bond. It's not stronger or weaker here actually. It's actually technically the same type. Okay, if this is the water molecule and this is one of the oxygen from the acid, this is the type of hydrogen bond really. I mean, you can find so many permutations here. This can belong to acid, this can belong to the water also. So the type of hydrogen bond formed technically is the same. So why is dimerization actually less favored when it's less favored, then your delta G is less negative? It's because, okay, I think I should go back to the question. What's my question? Sorry, let me find my question. It's about equilibrium position. I'll just use this one to answer it properly. Yeah, this one. Okay, the idea here is if you have a lot of water present, right, your monomer will want to form hydrogen bonds with water. Why? What's the reason? Is that it just have too many water. What is the chances of it forming together to form a dimer versus itself with water? When your water is like 1,000,000 times, don't know how many times more than the molecules of your peers. Chances are you will rather form molecule, you rather form the hydrogen bonds with water molecule. So all the monomer will rather stay put by itself. When that happens, that means your POH tends to the left already. But that's a picture already. Okay, since majority stays in this form, then your KC will now shift to the left. So your delta G to the right is less favorable, less spontaneous, obviously. Okay, that's the whole idea. The leftward delta G is more spontaneous, the rightward one is less spontaneous. So that's the idea behind this part. Is that okay? Right. Anyway, okay, I think I really had to stop here already. Okay, so thank you so much. Okay, the remainder question I have about 4, I think. Okay, I'll answer through the Google Sheet, and I still owe a bit of questions and response to some previous ones. Okay, anyway, that's it for me today. Okay, I'll stay here for a while more. If you have any questions, please come down. Okay, I'll see you next week. Thank you.